Hey Amber, I've been having some trouble with physics lately. Do you think you can help me?
Yeah, I can, Julie. You just have to fully immerse yourself in the subject. A fluid is a collection of molecules randomly arranged and held together by weak cohesive forces exerted by the walls of the container. Includes liquids and gases.
When an object is partially or fully submerged in a fluid, the fluid exerts on the object an upward force called the buoyant force. According to Archimedes' principle, the magnitude of the buoyant force is equal to the weight of the fluid displaced by the object. Say go!
Go! How much water does Julie displace when she jumps into the pool? In this diagram, the gravitational force is pulling Julie down while the buoyancy force is pulling her up. The force in the y direction is equal to 0, causing the buoyancy force to be equal to the gravitational force. The equation is the density of the fluid times its gravitational constant times the volume displaced equals the mass of Julie times the gravitational constant. The density of the fluid, which is water, is 1,000 kilograms divided by meters cubed. From the given equation, plug in your knowns and solve for the volume displaced. Go.
Pascal's law deals with the pressure of fluids at different heights. P naught is the pressure when H equals 0, and rho is the density of the fluid.
What is the pressure on Julie if she goes 3 meters underwater? Air pressure is 1 atmosphere. Pressure in varying depths equation is presented below. P naught is air pressure, which equals 1 atmosphere equals 1.013 times 10 to the 5th pascals. Density of fluid, which is water, is 1,000 kilograms divided by meters cubed, and H is the depth that Julie went. Taking the given equation, plug in your knowns and solve for pressure. Go.
Hey Amber, I was thinking about something. Why is it that when you jump into a pool and go deep underwater, why do your ears hurt? What's up with that?
This equation explains it. When you got pressure equals force over area, in the particular case that you have, it's a larger force on a smaller area. So your eardrum is a small area, and when you jump in a pool, you got a large force causing a higher pressure, which causes your ear to hurt.
What?
What is the pressure on Julie's eardrum if the radius of her eardrum is 4.3 millimeters? To find the pressure over Julie's eardrum, we use P equals F over A, where pressure equals force over area. Force is equal to Julie's mass times gravity, and the area is just the area over a circle. We plug these values back into the equation, and this equals 9,108 kilopascals. Holy crap! No wonder Julie's eardrum hurts so much.
Hey,
of the chimney, and the pressure decreases, allowing the hot air to rise. Ho ho ho! Wind at 20 kilometers per hour blows over the 12 centimeter diameter opening of a chimney. The box where the fuel burns is 1 meter by 1.5 meters. What is the pressure difference in the chimney? The best way is to use dimensional analysis, where we obtain 5.56 meters per second. Using the Bernoulli equation, we can plug in the velocity found and solve for the change of pressure. That is P of B minus P of T. Once we rearrange the equation for P of B minus P of T, we can plug in our knowns. After that, it's just simple calculation. We find that our pressure difference is 15.5 kilopascals. Boy, traveling around the world really makes me parched.
Do you need water, Santa?
I really do, Julie.
Luckily, there's a sink right here.
I have a cup. I love water. The water pressure is too high. Why is that, Julie?
Well, the nozzle area is so small that to fit the equation of continuity for fluids, that means that the speed of the water coming out is much greater than you would expect.
Oh no.
I know where we can get better water. To the hideaway.
Whoa, that was crazy. How fast is water coming out of the faucet? Here's a diagram of the sink in the physics lab. R1 is the bigger radius, and R2 is the smaller radius. This is the law of continuity for fluids. A1 times V1 equals A2 times V2. The first area is bigger than the second area. So, to compensate for this change, V2 is going to have to be a lot larger than V1, making it come out a lot faster than what you would expect. Here we have the same equation, the law of continuity for fluids, and we've just plugged in our known values for R1, R2, and V1, and then we solved for V2.
Go.
Look, Santa, this faucet will be better because it has a larger area, so the speed of the water will be slower.
You're so right, Julie. I love water. Now this speed flows way better. How fast is the water flowing from the sink in the hideaway? This is a diagram of the sink in the hideaway. The faucet has an inner radius of 0.5 centimeters and an outer radius of 0.125 centimeters. This radius is 2.5 times larger. Due to this size difference, V2 can now be a lot slower to compensate. We use our equation for continuity of fluids again and find that the new speed coming out of the faucet is 0.48 meters per second. This speed is much better for Santa. Now let's thank Santa for all his help. But oh no, Santa ran out of gas. How will he get back to the missus? That's alright. He'll just borrow some gas from the nearby sedan in the parking lot. He'll use a siphon to obtain this gas. Siphons are tubes which draw fluid over the rim of a tank to a lower point, after initial pressure change to initiate the flow, which he'll do by sucking on one end of the hose. This will operate continuously due to the pull of gravity. Torricelli's law, which is a derivative from Bernoulli's, says if a liquid flows from an opening in a container, its speed is the same as the speed of the fluid that would flow if it dropped free fall from the top of that container.
My face above the water, my feet can't touch the ground, and it feels like I can see the sands on the horizon every time you are not around.